Hi children, this slide presentation explains dominance and pareto-optimality. So before going to explain the different techniques for identifying dominated solutions or the optimal solutions, let's see some special solutions. The first one is ideal objective vector. So it is assumed that there exists one different optimal solution for each of the m conflicting objectives, and these individual optimal objective values constitutes the ideal objective vector. So this is the formal definition for ideal objective vector. So the mth component of the ideal objective vector z star is the ideal objective vector. Its mth component is the constrained minimum solution of the objective function minimize fm of x subjected to x belongs to S, where S is the search space. Fm is the mth objective function. So if the minimum solution for the mth objective function is the decision vector x star m with function value f star m, then the ideal vector is f star or z star is f1 star comma f2 star up to fm star transpose, where fi is the ith minimum, fi star is the ith minimum solution for the ith objective function. Actually, the ideal objective vector corresponds to a non-existent solution. Why? Because minimum solution of equation for each objective function need not be the same solution. So the only way an ideal objective vector corresponds to a feasible solution is when minimal solution to all objective functions are identical. If so, then those objective functions cannot be conflicted to each other. But in reality, in optimization techniques, we are considering conflicting objective functions. So this is the pictorial representation of the different solutions, special solutions, ideal solution, utopian and nadir objective vectors. So Z star is the ideal objective vector, Z double star is utopian objective vector, and this is the nadir objective vector, this point. This is the W is the worst objective vector. So ideal objective vector is actually used as a reference solution. So the solutions closer to this ideal objective vectors are better, and algorithms are they try to find out solutions which are very near to this objective vector. So the knowledge of lower bound on each objective function is required to normalize the objective values in common range. Then utopian objective vector. So a solution which has an objective value strictly better than but not equal to that of any solution in the search space is utopian objective vector. So this is the formal definition. So utopian vector objective vector is a double star has its components marginally smaller than that of the ideal objective vector. Mathematically, zi double star is equal to zi star minus epsilon I, where epsilon is the small value slightly greater than 0 for all I equal to 1 up to m, where m objective functions are there. Then utopian objective vector is also a non-existent solution. Now let's see nadir objective vector. So the nadir objective vector is represented as z nad. It represents the upper bound of each of the objective in the entire pareto-optimal set, but not in the entire search space. But W is the worst feasible solution value, where each component is fi max, f1, f2 up to fm max in the entire search space. So from the figure it is clear that here this W is the worst objective vector, but this is the neither vector. Neither is the upper bound of the objective values of the conflicting objective vectors, but W is the worst one. And neither objective vector is difficult to compute. So for consider two objectives f1 and f2, and z star of 1 is the solution, that is equal to f1 of x star 1, f2 x star 1 transpose. This is the solution of z1, and z2 is the vector f1 x2 comma f2 x2. This represents the coordinates of the minimum solutions of f1 and f2 in the objective space. But the neither objective vector is estimated as z nad is equal to f1 of x star 2 comma f2 of x star 1 transpose. Now let's see how it is represented in this figure. See, this z nad is f of z star 1 comma z star 2, where z star 1 is equal to z star 1 is x1 star f1 of x1 star f2 of x star 1, and z star 2 is f1 of x2 f2 of x2. So z nad is actually f1 of x2 comma f2 of x1. The neither objective vector represent sometimes existent or non-existent solution depending on the convexity and continuity of the pareto-optimal set. So it can be used in a normalization equation of objective functions. So in order to normalize these objectives in the range of pareto-optimal region, we can consider neither an ideal objective vector. So what is fi of norm? That is equal to fi minus zi star. Zi star is the ideal vector, ideal objective vector, the whole divided by zi neither vector. Zi nad is the neither vector minus ideal vector. So now let's see the concept of domination, or what is dominant solution. So dominant solution is required to find out the pareto-optimal solution. So we can explain this concept of domination using examples. So now let's see some concepts related to this domination. Assume that there are m objective functions. So the operator, this operator between two solution I and j is represented as I operator j. This represents the solution I is better than solution j on an objective vector. Similarly, I operator j for a particular objective implies that solution I is worse than solution j on that objective. So if an objective function is to be minimized, then this operator means that the less than operator, it's minimization. So if the objective function is to be maximized, then this operator represents greater than operation. Now let's see the formal definition of dominance. What is meant by dominance? So a solution x1 is said to dominate the solution x2 if both the conditions are true. 1 and 2 are true. What is condition 1? The solution x1 is no worse than x2 in all objectives. Consider all objectives x1 up to xn. Then the solution x1, then we have to compare, we have to do the pairwise comparisons of objectives. So the solution x1 is no worse than x2 in all objectives, or it can be represented as fj of x1 is no worse than fj of x2 for all j 1 up to m. That means m different objective functions are there. The solution x1 is strictly better than x2 in at least one objective. For at least one objective, x1 must be strictly better than x2. Then we can say that x1 dominates x2. Or we can represent this as fjx1 is strictly better than fjx2 for at least one j belongs to 1 up to m. So if any of the above condition is violated, then x1 does not dominate the solution x2. So it is required to satisfy both the solution to represent that solution as a dominant solution. So if x1 dominates the solution x2, mathematically we can represent this as like this. So it is then if you write x1 dominates x2, then we can say that x2 is dominated by x1, or x1 is non-dominated by x2, or x1 is non-inferior to x2. So we can discuss about this dominance using a case study. Here you can see two objective functions f1 and f2. f1 need to be maximized and f2 to minimize, and these two objective functions has 5 different solutions. These are given in this diagram. So that is explained in this slide. Two objective optimization problems with 5 different solutions. Objective function 1 needs to be maximized and objective function 2 needs to be minimized, and 5 solutions with the different objective function values. So we can discuss about the definition of domination based on this example. So domination can be used to decide which solution is better among the 5 different solutions. So and we can do this comparison using at a time we have to take 2 solutions to compare. That means pairwise comparison is used to find out the better solution. So if solution 1 and 2 are to be compared, then solution 1 is better than solution 2 in objective function 1, and solution 1 is better than solution 2 in objective function 2. So let's see how it is happening. We are comparing of 1 and 2, the solutions 1 and 2. So 1 is better than 2 because it maximizes the function f1 and minimizes the function, the objective function f2. So the solution 1 is better than 2. So 1 dominates 2. So according to the definition of dominance, we can say that the solution 1 dominates x2. Then we have to consider solution 1 and 5. See, 5 for objective function f1, 5 is better than 1, or its performance is pretty much equal to the solution 1, and for function f1, objective function f1, 5 dominates the solution 1, but for the objective function f2, the performance is comparable. 1 and 5, the solution 1 and 5 are comparable. So here also it satisfies the definition of dominance, and we can say that 5 dominates solution 1. Now let's see the properties of dominance relation. There are 3 possibilities that can be the outcome of the dominance between solutions 1 and 2, because solution 1 dominates solution 2, or we can say that solution 1 gets dominated by solution 2, or we can say that solution 1 and 2 do not dominate each other. These are the 3 things that can be inferred from the example. So now let's see the relation that we have just explained. So this binary relation, there exists a binary relation between the solution in the objective space. So these binary relation properties of the dominance of operator, whether it satisfies these properties or not. First one is reflexiveness, whether it satisfies reflexive property or not. The dominance relation is not reflexive because any solution P does not dominate itself. So we can say that it's not reflexive. And whether it is symmetric or not, this dominance relation is also not symmetric, because P dominates Q does not imply Q dominates P. Then about so if P dominates Q, then Q does not dominate P, thus the dominance relation is asymmetric. So whether it is antisymmetric or not. So since the dominance relation is not symmetric, it cannot be antisymmetric. Whether it is transitive or not, yes, the dominance relation is transitive. Why? Because P dominates Q and Q dominates R implies P dominates R. One more important property is that if solution P does not dominate solution Q, means this does not imply that Q dominates P. So the dominance relation qualifies as an ordering relation anyway. So we know that if it is reflexive, antisymmetric, and antisymmetric, reflexive, and transitive, it is a partial order relation. So the dominance relation is not reflexive and is not antisymmetric. So the dominance relation is not a partial order relation, but the dominance relation is only a strict partial order relation. Then comes pareto-optimality. To explain the pareto-optimality also, we have to rely on the case study. So we have to compare the solutions 3 and 5. Okay, so this is the diagram which shows this objective space and solutions. So we have to compare the solutions 3 and 5. So when you consider the objective function f1, 5 dominates 3. 5 is better than 3. But when you consider the objective function f2, 3 is better than 5. So thus the first condition is not satisfied for both of these solutions. The dominance equation, the dominance definition, the first condition in the dominance definition is not satisfied for both of these solutions. So cannot conclude that solution 5 dominates solution B, nor we can say that the solution 3 dominates solution 5. So we can say that solutions 3 and 5 are non-dominated with respect to each other. So for a given finite set of solution, we have to perform all kinds of possible pairwise comparisons, and we have to find out which solution dominates and which solutions are not dominated with respect to each other. And then we have to have a set of solutions, any two of which do not dominate each other. So it is possible to find a solution in the set which will dominate the set of any solutions outside of this set. So this particular set has a property of dominating all other solutions which do not belong to this set. So that set is known as non-dominated set. So in this example, solution 3 and 5 constitutes the non-dominated set. Now let's see the definition of non-dominated set. What is non-dominated set? Formal definition. So among a set of solutions P, the non-dominated set of solution is represented as P dash are those that are not dominated by any member of the set P, that is non-dominated set. So when the set P is the entire search space, that is P equal to S, the resulting non-dominated set P dash is called the pareto-optimal set. So the non-dominated set, if the P equal to set S, S is the search space, feasible search space, then the non-dominated set is known as the pareto-optimal set. So this is an example which shows all the possibilities of objective functions f1 and f2. So this is the diagram which shows the minimization of f1 and f2. Both functions need to be minimized, and this line shows the non-dominated region or the pareto-optimal region, and here in this diagram F1 need to be maximized and F2 need to be minimized, and here F1 need to be maximized, F2 need to be minimized. So this is both F1 and F2 need to be maximized. So in all these conditions, these are the four possible conditions of objective functions. In all these conditions we can find out the optimal set of solutions. Now let's see the globally pareto-optimal set. The non-dominated set of the entire feasible search space S is known as the pareto-optimal set or globally pareto-optimal set. So this is the formal definition of locally pareto-optimal set. For every member X in a set P, there exists a solution. There exists no solution Y dominating any member of the set P. Then the solutions belonging to the set P constitute locally pareto-optimal set. How can we say that there exists no solution Y which dominates any member of the set P? We have to compute the Euclidean distance of the of every member X with respect to Y. So if that distance is very less than the value epsilon, where epsilon is a small positive number, we can say that there is no solution Y which dominates any member in the set P. So then that set P is the pareto-optimal set or locally pareto-optimal set. So this is the diagram which explains locally and globally pareto-optimal set. Here you can see point B as locally pareto-optimal set, which is mapped to the point here. This is the solution space. You can see the point here. The global optimal set, pareto-optimal set, is the line which is represented in this diagram. Now let's see the strong dominance and weak pareto-optimality. What is meant by strong dominance? So a solution X1 strongly dominates a solution X2, or X1 dominates X2, strongly dominates X2, if solution X1 is strictly better than solution X2 in all M objectives. If solution X1 is strictly better than solution X2 in all M objectives, we can say that it is strongly, it is a strong dominance. That is, X1 is strongly dominates solution X2. So in this figure, solution 3 strongly dominates solution 1, since solution 3 is better than solution 1 in both objectives. Let's see. Solution 3, as far as F1 is concerned, 3 is better than 1, and 3 is better than 1, and for minimizing F2 also 3 is better than 1. So 3 is the 3 is strongly dominated than solution 1. Now let's see what is weakly non-dominated set. So what is weakly non-dominated set? So this is the formal definition. Among a set of solutions P, the weakly non-dominated set of solution P dash, weakly non-dominated set is represented as P dash, are those that are not strongly dominated by any other member of the set P. So weakly non-dominated set found from the set P represents the solutions that contains all the members of the non-dominated set. So weakly non-dominated set is required to find out the pareto-optimal set. So a pareto-optimal set is always a non-dominated set. There may exist non-dominated sets containing some pareto-optimal solution and some non-pareto-optimal solution. It is possible. So it is important that the non-dominated solution by the search algorithms must give emphasize that the non-dominated set of the given population must search to approach the true pareto-optimal region.